Hello guys. So this time we'll talk about a different trend in the periodic table, which is ionization energy. So definition for this IE or ionization energy is the energy needed to remove an electron from that atom in the gaseous phase. So for example, we have this equation. We have sodium atom in the gaseous state. Okay, going to sodium ion in the gaseous state as well, plus electron. So the energy involved is the ionization energy. So these ionization energies are all positive in sign. Okay, since we need to input energy to get the electron, since that electron is attracted to the nucleus. Okay, so let's have the trend. Okay. So as we can see, the ionization energies. So these are the first ionization energy. So when we say first ionization energy, so this is the energy required to get the first uh, valence electron in the atom. Okay. So as we can see, for the group A elements, so we have here as the highest in the helium, and then as we go down the group, as well as in this case, okay, there is a less ionization energy, and as we go across the period from left to right, there is an increase in the ionization energy. Okay, the first ionization energy, or the energy needed to remove one electron from the neutral atom, generally decreases down the group and increases across a period for S and P block elements, or the group A or representative elements. Okay. So, nope, not this one. Okay, so why is that? Okay, so first we have the down the group. Okay. So the valence electrons found, for example, in helium is found nearer the nucleus. That is why it is more attracted to the nucleus than the ones on the valence shell of the higher energy levels, such as xenon or radon. So this means that the farther the electron is from the nucleus, the easier it is to get that electron. Okay, because it will experience less attraction with the nucleus. Okay. What about if we have across a period? Okay. So this is still the same, is still with the same explanation with the atomic radius. So this is because in here, for example, in lithium, we have a positive 3 nuclear charge because of 3 protons. For neon, we have positive 10. Okay. We have positive 10 as the nuclear charge because of the 10 protons found inside the nucleus. So this means that on the neon atom, the electrons is harder to get since it is attracted strongly in the positive 10 nuclear charge than in the positive 3 nuclear charge of the nucleus in the lithium atom. Okay. So aside from the first ionization energy, we also have a trend on the second, the third, the fourth, and so on ionization energies. So when we say first ionization energy, so this is the energy to remove one electron in the neutral state. If we have the second ionization energy, so that is the energy required to remove the second valence electron. Okay, and as we see, there is an increase in the ionization energy from first to second and from second to third. For example, we have lithium. In lithium, we have 0.52 times 10 to the 6 joules per mole. And then on the second ionization energy, it is 7.30 times 10 to the 6 joules per mole. So it is larger. Okay. As you can see, it is larger in a bigger amount. And then we also have a bigger value for the third ionization energy. Take note, lithium only has 3 ionization energy since lithium only has 3 electrons. So ionization energy, or the first ionization energy, is required to get this first electron. The second ionization energy is required to remove this 1 electron from the 1s1. So take note, this IE2, or the second ionization energy, is applied after the removal of the first electron. The third IE, or the third ionization energy, is the ionization energy required to remove the remaining, or the last remaining electron in the lithium, making it lithium 3+. Okay. The same goes with this beryllium, boron, carbon, and nitrogen. So again, the succeeding ionization energies become larger, since the electron to be removed now becomes part of a positively charged ion. So when we have positively charged ion or cation, removing the electron is harder since it is located nearer now in the nucleus. So try to recall our discussion in the atomic radius and ionic radius as well. Okay, let's have a problem. Okay, using only a periodic table, arrange these atoms in order of increasing first ionization energy, or the energy required to remove the first electron. Aluminum, argon, chlorine, sodium, potassium, and silicon. Pause this video and then try to solve this using a periodic table. Okay, so let's have the answer. Okay, so the one with the smallest ionization energy is potassium, and then sodium, aluminum, silicon, chlorine, and argon. So based on the periodic table, this sodium, aluminum, silicon, chlorine, and argon are found in a period or across a period. So you'll just have to know their arrangement in the periodic table. So across a period from left to right, it goes Na, and then aluminum, and then silicon, chlorine, and then argon. And then the remaining atom is just potassium. So if you locate potassium, so that is found down the group together with sodium, and potassium is found on the lower part of the group 1A than the sodium. So this means that potassium has lower ionization energy than sodium. Okay. So this is the ionization energies for the elements in the periodic table and their trends.